Hello calculus fans and welcome back. Today's lecture is all about volumes. And what we'll see is that there are two ways to create a volume or to examine volumes. One is when we know what a cross-section looks like, when we can find the area of a cross-section. And the other is when we take a function and rotate it, usually around the x or y axis. So if you look at the picture that we have here, as we cut a cross-section perpendicular to the x-axis, we see that in each case we get an area. This is what we call a known cross-section, and that area is given by a of x. And so if we want the volume of this, all we do is just integrate this from a to b of a of x dx, because dx will simply give us a little bit of thickness and that'll create a volume. So that's pretty simple. Let's look at an example. Okay, so here's an example, and please excuse the pretty primitive picture, but we want to find the volume of a solid whose base is an ellipse, there it is, and whose cross-sections perpendicular to the x-axis are squares. Might not look like a square, but it's supposed to be a square. And so what we're going to do is find the volume of this. And so what we want to know is what the cross-section area is. Well, that's a square, and the height is 2 times y. And y, if we solve this, is going to be the square root of 1 minus x squared over 4 times 9. And we're going to integrate from minus 2 to 2. And so if you keep track of all that, here's what the volume is equal to. The integral from minus 2 to 2, going along the x-axis, of the height, which is 2 times the y value. So it's going to look like this. 9 times 1 minus x squared over 4, and then we get the little bit of thickness. And that's it. So as long as we know what the base is and what a cross-section looks like, these usually are fairly easy to handle. So my bad, this expression right here is just giving you one side. And so to get the area of the square, I need to take this and square it. So that's the way that should look. Alright, so for the second kind of volume, we look at what happens when we take a function and rotate it around the x-axis or the y-axis, or a line parallel to one of those. And in this case, there are two techniques. And the first technique is called the disk method, and that's usually used when we're going around the x-axis. Okay, so here's how the disk method works. Here's some function, and we want to find the volume when we look at the region from x equals a and x equals b and go around the x-axis. So the way I generally write that is the volume around the x-axis. And what we want to think about is a representative rectangle. Both of these methods, the disk method and then the shell method to come, are always made easier when you think about the rectangle. And if I take this rectangle and go around the x-axis, do you see that you get a disk, which is really a cylinder that's not very high at all? This is the height, f of x, and this is the radius, and this is the height, dx. So let me say that again. The radius of this disk is f of x, and the little bit of height is dx. And what we know is that in any case, the volume of a cylinder is pi r squared h. So once again, r is f of x, h is dx, and so this volume is simply going to be what we get when we add up all of those rectangles, which become disks. So we're going to go from A to B, and it's pi r squared, so I'll take the pi out. R is f of x squared dx, the little bit of height. And that, my friends, is the disk method. So let's put it into play. Okie dokie. So let's assume that we're looking at the function y equals x squared, and we're looking at the region under it from x equals 1 to x equals 3. And I'm going to take that region and go around the x-axis. And so the volume is going to be pi times the integral from 1 to 3 of the height, which is x squared, squared dx. So just to annotate this, this is my radius and this is my height. And what we have is the formula for the volume of a cylinder, which is pi r squared h. Pretty simple, huh? So we just want to note that this method is called the disk method, and usually used when we're going around the x-axis. But we'll see later on that sometimes we can use it when we go around the y-axis. Okay, so now let's try to visualize what happens if we have essentially the same type of region, but now we're going to take this region and rotate it around the y-axis. This takes a little bit more visualization. But again, the whole key to this is thinking about what happens if I take a rectangle like that and rotate it around the y-axis. What do I get? What you get is a figure that we call a shell. So you got to take a few seconds and think about that, what it looks like. It's kind of like if you take a piece of 8.5 by 11 paper in landscape mode and just kind of bring the edges together. And the way you find the volume of something like that is imagine that you cut the edges. Well, then you have one length, which is 2 pi r, another length, which is the height, and another length, which is the little bit of width. And what we can understand in this, when you think about it, is r is this dimension right here. And the height is this dimension right here. And the width is right there. And so if we rewrite it, the volume of this is going to be 2 pi x times f of x times dx, and that's a big deal. So therefore the volume of that shape when I go around the y-axis is going to be 2 pi. I'm going to take out the 2 pi. I'm going to go from A to B of the radius times the height times the little bit of thickness. And this is called the shell method. And of course, here comes an example. So let's consider exactly the same region. And what we're going to do now is take this region and go around the y-axis. And so again, you just think about one of these rectangles, and I can't overemphasize how important it is to just keep thinking about the rectangles. And when I go around the y-axis, I generate a shell, and so the volume is going to be 2 pi times the integral from 1 to 3 of the radius times the height times the little bit of thickness. And there you go. And that is, as we said before, this is the shell method. Alrighty? So two methods, disk method and the shell method for solids of revolution. Alright, so let's take a look at this picture. And now let's imagine that I'm going to take this region, this is a bounded region, and rotate it around the x-axis. What happens? Okay, so the way that we think about this is first we want to look at rectangles which go all the way up and rotate them around the x-axis. And then we want to go up just to the second one, the lower function, and rotate around and subtract. So visually, here's what we're doing. We're going all the way up and rotating that around the x-axis. And then we'll go up only this high and rotate that around the x-axis and subtract. And so, if I can write this out, it's going to be pi, because we're using the disk method, times the integral from 0 to 1 of the top function, which is x squared, minus the bottom function, which is x squared dx. And if you visualize what happens when we take just that much and go around the x-axis, which is really what we want, we're getting a figure that is called a washer. So the washer method is really just a special application of the disk method. It's really one disk, the blue disks, and then subtract the yellow disks. And that's what we get in a bounded region going around the x-axis. So suppose we take that same region, I'll make it a little bit darker, this rectangle right here, and I'm going to rotate that around the y-axis. Well, that's going to give us a shell, and the only change here is going to be in the height of the shell. The radius is still x, the little width is dx, and the height is just this much, which we have already learned to be top minus bottom. So taking that same region and going around the y-axis using the shell method will be 2 pi, we're integrating from 0 to 1, of the radius times the height, which is top minus bottom, times the little bit of thickness. And notice, please, that that is the shell method. All right, let's look at a few more examples. Okay, so let's really shake things up here. Let's look at the region that we're talking about now, and let's talk about the volume if I take that region and go around the x-axis. Right? So we know by the disk method that this is simply going to be pi times the integral from 0 to 4 of the height squared dx. Height or radius really should be. But how about if we think about this using the shell method? Well, in that case, what we're looking at are rectangles that look like this, going around the x-axis. And that was going to give us something which is going to look like this. By the shell method, we're going to get 2 pi. Now, we're integrating along the y-axis here. So it's going to be 0 to 2 of the radius, which is y, times the height, which is going to be right minus left here, 4 minus y squared, times the little bit of thickness, which is dy. So notice here that this is what we're talking about when we're talking about the shell method. That's my rectangle. This is my radius, which is y. This is my height, which is x minus y, or 4 minus y squared. And this is my little bit of thickness, which is dy. And I'm integrating along the y-axis, so I'm going from y equals 0 up to y equals 2. Get it? Kind of putting things on our head there. Okay, so now let's dive into this a little bit more. Let's talk about the same region, this region right in here, and now let's talk about it when we go around the y-axis. Well, traditionally, if we go around the y-axis, we're going to use shells, and this is going to be 2 pi times the integral from 0 to 4 of the radius times the height times the thickness. Okay, so no surprises there. But how about if we wanted this same volume, and now we want to use washers? Okay, so that's going to be pi times the integral from 0 to 2 of 4 squared minus y squared. That's what x is equal to y squared squared dy. So that's worth thinking about a little bit. Okay, so now it's time for you to do a little thinking, a little bit of work. Same picture, same as before. And what you need to try to work on is to figure out what the volume is when we rotate around the y-axis using shells, which is traditional, and then using washers, which is a little bit different. Similarly, let's imagine that we're going to go around the line y equals 5, something like this. And we'll use washers, which use vertical rectangles, but I also want you to think about what you get when you use shells, which is horizontal rectangles. So try not to look at this too much. Try to look right here, set up the problems, and then see if you can figure out how to get the expressions that I have. And finally, same region, but what I'd like you to think about now is what do you get if you take the volume and you rotate around the line x equals minus 1 using shells, which is vertical rectangles. But then try to think about how you would find it using washers, which means horizontal rectangles. So once again, if you can do this work without looking at the answers and see if you get the same result, then I think you're there. All right? So a lot of stuff to think about in this problem with volumes. See you next time.